Él la debería agrandar.
¿Puedes agrandar la
F5, Lucas.
Sí.
Modo presentación.
Can I start?
Modo. No.
Bueno, empezamos así.
Sí, pero
Voy a apretar F5, así se ve más grande.
Se está escuchando.
No, el micrófono está acá.
Lucas, ¿me escuchás?
Sí, sí.
Puedes poner modo presentación, no sé si es tecla F5 o control L.
Ah, ok.
Eso es lo más grande que...
Ok.
Ahora sí, perfecto.
Bueno, tenemos la última conferencia plenarias. Lucas Reis, de la Universidad Federal de Minas Gerais, que ahora está haciendo un postdoc ahí en Carleton. También. Y nos va a hablar de factorización de iteraciones de polinomios sobre cuerpos finitos. Muchas gracias y hablar.
Ok. Eu gostaria de agradecer a Ricardo por la invitação para dar essa charla. My talk will be in English since my portuñol no es muy bueno. Okay, so the talk is about factorization of iterates of polynomials over finite fields. This is partially based on joint works with Arthur Fernandes is my PhD student from Federal University of Minas Gerais, Daniel Panario and Stephen Wan, both from Carleton University. Okay. So I'll just start introducing the objects we are going to discuss throughout the talk. So we consider K a field, and F and G two polynomials with one variable over this field K. And then we consider the following construction of polynomials. So we start with a polynomial T0, which is just a polynomial F. And then we start composing F with G. So we take iterates of G and start composing, right? So here is an F, it should be T instead of F. And so basically from this construction, we obtain this sequence of polynomials. So F composed with G, F composed with G, composed with G again, and so on. So we are just starting with F, and then we replace X by G of X. And well, in fact, we can provide a similar construction, replacing the polynomial G by a rational function. So how is the construction? We start with a rational function Q with coefficients in the field K. And so we consider the iterates of Q. We write as a quotient of two relatively prime polynomials over K. So little hn and capital Hn. And then we construct in a very similar fashion a sequence of polynomials. So we start with F, and then we start replacing X by this rational function at each step of the process. But well, in general, if we do this, we won't arrive at a polynomial, right? So if we compose F with the skew n, basically we will obtain a polynomial divided by the denominator of the rational function Qn, which is Hn power to the degree of F. So when we do the similar construction that we started with polynomials, in the case of rational functions, we also multiply the composition by this polynomial, capital Hn to the degree of F, right? So this makes this expression a polynomial again, right? And so observe that this is the natural extension of the of the case of polynomials, because when Q is a polynomial, so age n is always 1, right? So we are just, this factor here doesn't appear, so we are just doing the same thing we're doing at the initial setting, right? Okay, so we just consider one of the two sequence that we're discussing, right? Composing with polynomials or rational functions. And so we have here two main questions in a context of arithmetic of polynomials over fields. The first one is the irreducibility of these iterated polynomials. And the second one, well, if the polynomial is not irreducible, what can we say about the factorization of this polynomial into irreducible factors over the field K? Okay, so these are the two main questions we are going to discuss in this talk. And basically, we are going to focus on focus in a case where the field is finite, but there will be, I will just mention a few works there basically deal with more general settings. Before proceeding, I'll just give an outline of the talk. So we're just discussing these two questions, but more specifically, we discussed the reducibility of all iterates of polynomials. So we start with a polynomial f and compose with the same polynomial f, right? So this is basically the initial setting here, where g equals f, right? And so in this part, we are going to discuss, under what conditions we can guarantee that all these iterates are irreducible over the field. And the second question is about the statistics for the factorization of polynomials of this first type I defined. So in this case, we are basically considering the case where this is not irreducible. And so if it's reducible, what can we say about the factors, right? And finally, this third topic, we just discussed the construction of irreducible polynomials by rational transformations. So this is the context of the second type of polynomials. Okay, so we just start with the first part. We actually have a name for that. So if I take a polynomial f over a field k, this polynomial is called stable. If stable over the field, this is important, over the field k, if all the iterates of f are reducible over k, right? And so there is a very simple remark here that is important. We are asking for all the iterates to be irreducible, but it turns out that if some iterate of f is reducible, so I can find a non-trivial factorization, then all the following iterates will be reducible as well, right? So if I write my f composite with fk times as r times s, both of them of positive degree, I can write any following iterate in the same way, right? So basically, if at some point some iterate of f is reducible, all the following will be reducible as well. So basically, we obtain an equivalent definition of stability. So I could basically replace like all iterates are irreducible by infinitely many iterates are irreducible. And so basically, in a context of the arithmetic of iterates of polynomials, this is the most discussed question in literature. Is the stability, right, of polynomials. So I start composing the polynomial with itself and ask for the irreducibility of this sequence. Here we have some past works. First one, this is a work of Ayad and McWilliam. They basically discussed the irreducibility of iterates of quadratic polynomials over general fields. They basically obtain some necessary conditions for the stability of these polynomials, but they also discuss some sufficient conditions in a case where the field, the underlying field is the field of rational integers. There's also this work from 2002, Danielson and Fine. that the main subject is binomials, right? So they discuss the reducibility of iterates of binomials. Most of the work is over infinite fields. There are some general lemmas there, but most of the work is over infinite fields, emphasizing two very particular cases, the case of rational numbers and the case of rational functions. So basically we have, in the case of rational functions, the coefficients of the polynomial are elements, are quotients of polynomials in another variable. And finally, there's this work of O'Donnell, 1997, that he basically studies the irreducibility of iterates of additive polynomials. So automonomials appearing at powers of the characteristic. So it's a field of positive characteristic. And the coefficients now are, again, rational functions in a certain number of variables in a way that they are independent. So we don't have like relations between the coefficients, right? So this is what I mean with generic. So, and basically in this work, he was trying to understand the Galois group of the iterates of these polynomials. And basically he's able to prove that the iterates of additive polynomials in this setting, they are all stable, and he's also able to compute the Galois group of the iterates. More recently, there's this work there's actually now exploring the non-stability, right? So proving that some polynomials are not stable. So some composition, some iterate will be reducible. And at the end of the paper, they proposed this conjecture that this polynomial x cubed plus x squared plus 1 is stable over the binary field, right? And this was recently proven in 2023 by Lin and Wang, that this polynomial is indeed stable, right? So considering the setting, right, of stable polynomials that are just taking iterates of a function, right, this reminds a lot of dynamics, right? It is natural to expect that some, results on stability of polynomials will be related to dynamics. And so there is this result from 2011, Jones and Boston, that they basically provide a very nice criteria for the stability of quadratic polynomials when the field is finite and of odd characteristic. So here's the criterion. We have Q an odd prime power. F of x is a quadratic polynomial with coefficients a, b, and c. And basically, the criterion relies on looking at the iterates of f as a function, right? So we are looking at the iterates of f as a map, right? At the point gamma, which is basically the critical point of this quadratic polynomial, right? Minus b over 2a. And so the criterion basically says that the polynomial f is stable if and only if the set, which is called the adjusted post-critical orbit of the critical point, which is composed by these elements, right? So minus a times f evaluated at gamma, union with all the iterates of order 2 and above at the point gamma. All these elements must be non-squares of fq star, right? So they are all non-squares of the field, and they are non-zero, right? So observe, of course, that since my field is finite, this set is finite, right? There is this representation I at least 2. At first glance, this could be infinite, but we are working with a finite field. So this is a finite set, right? So basically, in order to explore the stability, right, which is at first glance is something infinite, right? We need to compose f all the iterates and check if it's reducible. This reduces to check if a finite set contains only non-squares or fq star. And basically, like a few months after this paper was published, actually there's a difference. This was published in 2011, and there was also following work on this result by Ostaf and Shiparlisky. And basically, they studied this set, right? of the iterates of f at a critical point. And they basically proved that the number of elements in the set, they provided a non-trivial bound for the number of elements in the set when the polynomial f is stable, right? So if f is stable, this set cannot be too large, right? A trivial bound here for the size of this set is q, right? Because all the elements are in fq. But they actually proved that this is at most of order of q through 3/4, right? Provided that f is stable. So combining this bound, they basically provide a very simple algorithm to test the stability of quadratic polynomials and they bounded the complexity of this algorithm, right? So the idea is quite simple. It's easy to check if an element is a square or not, right? We have Euler's criterion. And so basically, the complexity relies on how many elements we need to check in order to decide if a polynomial is stable or not. Okay, so motivated by these two works, this is a result from 2023. In a joint work with Arthur Fernandes, my PhD student, and Daniel, we basically extended this criterion for binomials over finite fields of any characteristic. So I'm not going much into the details. I would have to define some objects, but basically we obtain something in a very similar shape when compared to Jones and Boston paper. And basically we have this a binomial x to the t minus b is stable over fq if and only if, well, we have some conditions on t and q minus 1. There are some divisibility conditions. And also this set, which is very similar to the other one considered for quadratics, the elements in this set satisfy a special property, right? And so this is very similar if we look like we are just evaluating iterates of f at 0. And 0 is exactly the unique critical point of this polynomial, right? And in fact, when t is equals 2, we just recover Boston and Jones result, right, for quadratic polynomials. And more than that, we also went through the work of Shiparlinsky and Ostafi, and we also provided a non-trivial upper bound for the size of this set when the polynomial, right, f of x, this binomial, is stable over fq. Okay. So, and actually, as a very nice application, basically we obtained some instances where this set actually reduces to only one element. And I mean, this is possible, right? All these elements here coincide, right? So in this case, we obtain some restrictions, but we are able to obtain a family of stable polynomials that we don't need to do anything, right? So the theorem just says this is stable over a prime field, right? So basically, if P is 5 mod 24, then this quartic x to the 4 minus 2 to this exponent, which is an integer, this polynomial is always stable over FP. Okay, so I'm just briefly commenting on the tools, right? So the general framework for proving the stability of polynomials is based on Capelli's lemma, right? Which basically tell us when the composition of two polynomials is reducible, right? So if I take f and g, two polynomials, then the composition of f with g is irreducible over a finite field, over a field k. Here the k is missing, sorry. So the composition is reducible over the base field k if and only if the polynomial f itself is irreducible over the field k. And now, well, knowing that f is reducible, I take alpha as a root of f in some extension of k, right? I take the smallest extension containing alpha, so k of alpha. Now I look at this polynomial g of x, which is the inner polynomial in the composition, and then I consider G minus alpha. This is a polynomial over K alpha, right? And so this polynomial must also be reducible over this extension. So, and this is basically the main tool. And most of the results that we have, like proving the stability of polynomials, so the theorems on the positive that this polynomial is stable, or this polynomial is stable if and only if something happens. All of them are basically using Capelli's lemma and induction, right? Because induction is natural in a problem, right? We're taking iterates of polynomials. So we have this basic setting. And in fact, the main abstraction is on the inductive step, right? So we're going from n to n plus 1. And basically, we need to discuss, right, in the case of stability, so G and F are the same, we need to discuss the irreducibility of translates of my polynomial F, right? And basically, most of the results that we find in the literature, it's based on things that we know, right? We know when a binomial is irreducible over a finite field or a general field, and the same thing for quadratic polynomials, right? Okay, so in the second part, we are moving now to the composition of it's the same construction as before, but now F and G are not necessarily the same. And now we are interested in the factorization of this expression, right? So this is the sequence of polynomials. We start with F and then start composing with G, right? And basically here we discuss the factorization of these iterates. So I consider, right, the expression Tn as the product of distinct irreducible factors, distinct irreducible polynomials over Fq, right? So there could be some multiplicity, some number of polynomials. And in this part, we are mainly interested in the behavior of some arithmetic functions. They are basically measuring some properties of this factorization, right? So I have here the function delta n, which is just the number of distinct roots of the iterate. N of n is the number of distinct irreducible factors. M of n is the largest degree of an irreducible factor. And A of n is just the average degree of the irreducible factors of my iterate, right? So here, all these functions are depending on n, right, which is the order of the iterate of my process. So one remark here that we can actually relate this to stability. When F and G are coincide, right, so we are just iterate the same polynomial. My polynomial F is stable if and only if the number of distinct roots coincides with the degree of the iterate, which is just the degree of F to the power of n. And so we are basically here, we are going to discuss these arithmetic functions in a sense of growth, right? So as n goes to infinity, how is the behavior of these four functions? So basically we have some trivialities, right? So in some cases, this behavior is quite trivial, so it's not interesting to explore. For instance, if f is a constant or the degree of g is at most 1, then when we start, right, the construction of this sequence, all the polynomials will be of bounded degree. So all the functions will be of bounded degree, so it's not interesting to explore this case. A similar phenomena happens when g is not of degree 1, but a power of degree 1, where this power is a power of the characteristic, right? So basically, this is another critical case. And so in this case, we can also verify that all these arithmetic functions we are considering are all bounded by a constant. So it's not interesting to discuss the growth. And finally, there is another case, it's this is actually more related to dynamics, because basically here we have a conjugation of my G by a map X minus A. And in this case, we also have a triviality, right? If F is of this form and G is of this form, all the iterates will follow a very trivial pattern. And again, all the arithmetic functions will be all bounded by a constant. And so in all these cases, we just say that the pair FG is critical. So basically, when the pair is critical, it's not interesting for us to discuss the growth of the arithmetic functions we are considering. So for instance, we already assumed F is not a constant and G has degree at least 2. So we are generally out of these cases. So, well, in order to state the results, we just need some notation from asymptotic analysis, right? So if I have A and B here, two arithmetic functions, I have this notation, right? B is has the growth type of B is larger than A, right? So if this inequality holds from some C, positive C, and A is little o of B if the quotient, right, goes to 0 as n goes to infinity. And also we put A and B similar. They have the similar growth type if we have these two conditions at the same time, right? So A and B, one is big O of the other. And so in this paper from 2014, Gomes, Pettis, Ostaf, and Shiparlinsky, they studied these questions, right, for the case F equals G. And they obtained this theorem. I'm not going much into the details, but basically they start considering the set of all polynomials of degree D, right? So recall that we are considering F and G the same, right? F equals G. So I take the set of all polynomials F of degree D, right? And so all these results in a theorem, they hold for all but a small proportion of all polynomials of degree D, right? So we are excluding this amount of polynomials, which is irrelevant if Q or G goes to infinity. But apart from this very small set, irrelevant set, we have these properties, right? So when I start iterating F, the number of distinct roots of the iterates would grow at least something like linear. The number of irreducible factors will also be bounded by a linear function, right? Provided that n is not too large when compared to q, right? So here we actually have a q and n must be moving. And then we get this lower bound, right? And finally, well, unless f is of a very strange form here, ax to the d, then the largest degree of an irreducible factor of the iterates of f must grow at least linear with respect to n, right? So we have this lower bound. So basically, well, in trying to simplify here what the theorem is saying, that most of the polynomials of degree D, right? I forgot to mention, they actually require that the degree is relatively prime to the characteristic. This is important there. If D is relatively prime with Q, then roughly all these three functions, number of distinct roots, number of distinct irreducible factors, and the largest degree of an irreducible factor, all of them grow at least linearly with respect to n under some conditions. Under some extra conditions, if, for instance, we consider the function n, right? And so just one comment on a proof, right? They basically use some character sum methods on proving the results. Basically, they work with the discriminant of the polynomial, right? So basically, it's hard to compute the discriminant of general polynomials, but we know that this will be a multivariate polynomials if we look at the coefficients of the polynomials as variables, right? So basically, they work with this approach and using character sums, right? That's why they needed this condition, the GCD between G and Q equals 1. Because at some point they will use Weyls bound, right, for rational points on curves, and this is an important tool. And so basically motivated by this work, I in 2020 I studied some further properties of these polynomials, but with a very different approach, right? So I didn't use character sums at all. It was a very basic approach, trying to use Capelli's lemma. And so basically we have a very extension of Capelli's lemma, because Capelli's lemma is about irreducibility of compositions, right? So there is an extension of this result that says like, okay, what if this composition is not irreducible? How can we know the factorization of the composition of two polynomials based, right, on the composition, on the factorization of this polynomial, right? I take the inner polynomial minus a root of f, right, as in Capelli's lemma. So basically we have a very nice structure. If I factorize this inner polynomial minus alpha over the extension field, I get a very, not very similar, it's the same pattern of factorization for the composition over FQ. And well, one of the main advantages is that with this approach, I was actually able to prove that the number of distinct roots of iterates grow exponentially, right? So it's very far from the lower bound they provided, which is linear, right? And so this is compiled in this theorem. I'm not going much into the details. So basically, as I say, we proved that the number of distinct roots grow as an exponential function. And actually, we can go further, right? So if I take my little g, I basically write the g in a very specific form. So I basically simplify the polynomial. So I remove all the trivial powers that might appear, which is related to the characteristic, right? So this is basically to look at the, in a proof, we have to look at the derivative of polynomials, right? So if a polynomial is a perfect power, with the power being something divisible by the characteristic, the derivative is vanishing, right? So we need to remove this triviality. And so basically, we actually proved that not only grows exponentially, but it's like growing like the degree of this inner polynomial capital G, right? So I take my little g, factor out everything with try to put as this exponent as a power of p, right? At the inner, well, we would just have like a polynomial capital G to the power p to the h. And well, we are assuming since the beginning, right, that my little g is not a linear polynomial to p to some h, right? So I know that my capital G is not linear. So it has degree at least 2, right? So if I call this degree d, I prove that the number of distinct irreducible factors will grow like g to the n. As a consequence of that, actually the largest degree, right, of the iterates will grow linear in general, right? So this linear growth is the smallest possible for this very general situation. And well, this third result is just a corollary from the first bound. So at each step, either the number of irreducible factors or the average degree of the irreducible factors has an exponential lower bound, right? So the proof that basically everything is about the first item, right? It's something actually already expected. We have a more general contest of rational maps on the projective space. And there are like a theorem from Hurwitz, for instance. You can use the, you can expect that the number of roots will grow exponential when you start iterating a rational map. So the idea is very similar. We just need to detect the critical points in the pre-image of some elements in the algebraic closure. And critical points are bad because at critical points we get less pre-images than expected. But apart from all these cases, we actually proved that at some point the number of pre-images will become exponential. And so this is what I said before, right? The bound for this third item just follows from this equality, right? Delta n is just an times n of n. And for the largest degree is just like a combinatorial argument, right? If I find m of n, I know that all the other roots of my polynomial will be in one of these extensions: fq square, fq cube, until fq to the largest degree, right? And so it's just a basic counting argument to prove that mn has to grow at least linear with respect to n. And so in the rest of the paper, we just focus on examples, right? So families of polynomials where we can actually describe the growth of these functions. And just to mention, this is highly non-trivial, right? Because we can barely compute the iterates of these polynomials. So the question about factorizing these polynomials is even harder, right? So here we take very special cases. So we are taking f composed with iterates of g, and my g here is either a monomial or a q-linearized polynomial, right? So it's a very special class of additive polynomials. The coefficients are in fq, but the monomials appearing are also of degree a power of q, not just a characteristic, right? And so for these two cases, it's very basic, it's very straightforward to compute the iterates of these polynomials. We have very simple formulas for computing the iterate of g when g is one of these two forms. And in fact, we have also the factorization of these compositions, right? So it's obvious that if I compose a monomial with itself, I get another monomial, and the same thing happens to q-linearized polynomials. For the case when G is a monomial, it is a very classical result, right? We have the finite fields book gives a criterion for the reducibility, but we actually have something more general, right? If I compose F polynomial with a monomial, I know precisely the distribution degree of the reducible factors. So I know how many of them of each degree, right? This is very old result. And basically, in 2018, I provided a very analog of this result for the case of q-linearized polynomial. This is very interesting because we have a very, I basically provide a theorem that is just a translation of this result of Butler, right? And in the result of Butler, it appears many arithmetic functions over Z. And in the case of linearized polynomials, it appears a lot of arithmetic functions over fqx, right? Which is, as we know, right, the natural analog of z, right, is the set fqx. And so using these two results, right, it's a lot of computations, but we get very nice insights about the growth of the arithmetic function. So for the case when where g is a monomial, we note that the largest degree of an irreducible factor of the iterates, we always grow exponentially, right? So we only have one type of growth. But now for the number of irreducible factors, this can grow as any polynomial, right? So this can be bounded, which means that eventually it's constant, the number of irreducible factors. This can go as a linear function in n, as a quadratic function, cubic, etc., right? And not other growth is possible, right? So we only have polynomial growth. And so as a corollary, we prove that, we just obtained that the average degree of the irreducible factors in this case always grow exponentially. And this is very interesting, considering now the case of q-linearized polynomial, we have a very contrast to the previous result. So now when we consider q-linearized polynomial, the number m of n always grow linearly, right? And as a corollary, the number of irreducible factors grow exponentially, right? So in the case of Q-linearized polynomials, when we start iterating, right, a polynomial, a composed polynomial with the iterates of a Q-linearized polynomial, I get usually the factorization is like lots of irreducible factors, all of them of very small degree. And the average degree of the irreducible factors also grows linearly. And at the very end, the idea was actually to combine these two G's, right? So I compose a linearized with a monomial. So I get this hybrid polynomial. And in this case, for this polynomial, both the largest degree and the number of irreducible factors, they will both grow exponentially, right? So basically, we obtain this table, all the possible growth of these functions, right, given by the examples. Here is given by the theorem, if it's this bound in the theorem is either optimal or not, and some examples, right? Okay, so here are some open problems. We have, for instance, there is this result, right? The largest degree of an irreducible factor grows at least linear, right? Linearly with respect to n. So it would be interesting to find all the polynomials G attaining this bound, right? We note that for linearized polynomials, this bound is attained, but are there any others? So this is an open question. The second one is actually more a guess. I was just trying to find something in between. I was not able. And so I believe that there's no intermediate growth, right? So either the largest degree grows as linear or will grow at least exponentially, right? So there's nothing in between. And finally, we observed here that as a very simple corollary from the main theorem, at every time, every step I'm doing the iterate, either the number of irreducible factors or the average degree, one of them is bounded below by an exponential function. But we cannot take a uniform bound, right? So it could be that n, at some point, n is growing really fast and then stops growing, and then a grows really fast and then stops growing, and they just like keep changing the growth, right? But I believe that we can actually find a uniform bound for at least one of them, right? So one of them must grow exponentially. Okay. Yeah, actually there are further comments on this part, but since I'm running out of time, I would just skip this part. And so finally, this third part is about the construction of irreducible polynomials by rational transformations. So we go back to the initial setting, but now I replace G by a rational function, right? So I consider Q a rational function with coefficients in FQ. And then I take the iterates of Q, right, as a quotient of two relatively prime polynomials, little h, capital H. And then I construct the sequence as before, right? So I always replace x by q of x, but now I have to multiply my expression by capital H of n to power the degree of f in order to have a sequence of polynomials, right? So in this case, we are interested in the pairs FQ for which all the iterates will be irreducible, right? So this can be somehow a natural extension of the stability of polynomials, right? So we are taking iterates and ask for all of them to be irreducible, right? Of course, if Q is a polynomial, we're just back to the previous setting, right? As I mentioned before. And so in this part, we discussed two main questions, right? So given Q, a rational function, and an integer d, how can we find a polynomial f of degree d such that the first iterate is irreducible, right? So I compose f with Q, and this is again irreducible. And the second one is about the I don't know, how effective is this procedure of composing with Q, right? So if at some step I have an irreducible factor and I go to the following step, how can I guarantee that the next polynomial will also be irreducible, right? So the main tool, again, is just an extension of Capella's lemma. I'm not going into the details. It's just very natural extension of Capella's lemma. And well, this, just to mention, right, it was not like, this problem was not discussed in this very general setting, right? Because this is it's something quite, the problem is quite general, right? But there are families of rational functions that we have some results, right? The first case is when Q is a monomial, so this is quite trivial. We know, right, when a composition of a polynomial with a monomial is reducible, right? This is a very classical result. Well, this second result is due to main, right? Actually, this has some application, right? Some motivation of constructing a chain of finite fields, right? So in this case, my polynomial Q is of degree, my rational function is of degree 2. And so basically, in this case, the author constructs a sequence of self-reciprocal irreducible polynomials, right? And the degree is just being multiplied by 2, right? And finally, there's this case of in 2012, right, when my rational function is just a quotient of two polynomials of Artin-Shiraya type, right? And so in these three works, we have, in these three cases, we have necessary and sufficient conditions for the reducibility of iterates of this rational transformation. So there's something very interesting among these classes, because they all have a very interesting property, right? The rational functions considered there, they are all invariant by the action of Mabel's transformation, right? So the case of x to the t corresponds just by a multiplication by a constant, right? And actually, if we look the correspondence between Mabel's transformation and elements in the projective general linear group, right? The case x to the t basically corresponds when the case that up to conjugation where my matrix is diagonal, right? The case x plus 1 over x corresponds to a very basic involution, which is a matrix, right, of order 2. And the case of this rational function, quotients of two Artin-Shiraya polynomials, corresponds exactly in a case where my matrix is has two equal eigenvalues, right? So it's a Jordan block of size 2. And well, this was actually in my PhD thesis was a topic of interest, studying rational functions invariant by Mabel's transformations. And well, we actually stepped out in a very interesting class of rational functions when we consider the case where A is not diagonalizable over the base field FQ. So I'm not going much into the details, right? But in this working with Stephen and Daniel, we obtained this this family of rational functions, right? There are some conditions here. The degree is always a divisor of q plus 1. And theta here is just the root of this polynomial, right? The parameter here is c, an element of fq. And this polynomial is irreducible. And so there we discuss the two issues I started in the section, right? So given how to find given d, how to find a polynomial f of degree d such that when I apply this rational transformation, I get an irreducible polynomial, right? So one of the things I proved in another paper is that if my rational function has degree d, then this is actually a random result, right? So I don't know how to find the polynomial f at first glance, but I know that a lot of them would make the job, right? So actually, phi of d over d, a proportion of phi of d of the monic polynomials of degree d, would make this first step produce an irreducible polynomial. So basically, this gives us a random method, right? I draw a polynomial of degree d and check if it's irreducible, the rational transformation. If it's not, I try to pick another one and so on, right? So there are some very interesting cases, right? For instance, if D is a large prime, this quotient is pretty close to 1, so I need, assuming independence in this event, right? In these events, I can draw only a few polynomials f of degree D, and at some point I would already get one that is irreducible, right? And just to mention, of course, it's really easy to check if a polynomial is reducible or not, right, over a finite field. And second, we just discussed the efficiency of a procedure to keep doing this rational transformation and obtain a sequence of irreducible polynomials. So actually, we proved that if my initial polynomial f has even degree, or the degree of my rational function, capital D, is not 2 mod 4, then once I get if the first polynomial is irreducible, all the others will be, right? So this is very efficient because I only need one step to verify all the others under these conditions. And actually, on the complementary case, if D is odd and D, capital D is 2 mod 4, we actually believe that this is never efficient, right? So if the first guy is irreducible, I apply the rational transformation. The second polynomial will actually split in 2 irreducible factors of the same degree. We weren't able to prove that, and so we just proposed it as an open problem. But well, in this paper there was something very important missing. We didn't discuss like necessary and sufficient conditions in order for the first polynomial T1 to be irreducible, right? So and the point is that the main challenge was that the rational function was too general, right? So it has this parameter theta and capital D, right? But it would be interesting to consider, you know, some specific constructions. I think even one example, like giving one C such that this is reducible, compute the order of the matrix, and obtain the explicit expression for the rational function, right? And try to discuss necessary and sufficient condition for the reducibility of the first iterate, right? So we can actually get a very strong theorem, right? In the paper with Daniel and Steven, we actually provided examples, right? So because we are basically applying this random method, right? So we use a program to draw polynomials and do this. But it would be interesting to obtain something like a theorem, necessary and sufficient conditions, in order for the first iterate to be irreducible. And so, well, I believe that any approach we go through discussing the reducibility of these polynomials, right? I take my rational function, so numerator minus beta times denominator, where beta is in some extension of FQ, right? And actually, this is very interesting because we only have few families in the literature that we can actually describe, right? We have a very simple criterion on the reducibility of polynomials of this form, right? And so this actually covers all the quadratic rational functions, some cubic rational functions, binomials, and Artin-Schreier polynomials, right? Okay, I'll stop here. Thank you very much.
¿Preguntas? ¿Comentarios? Bueno, agradecemos a Lucas, nuevamente. Y tenemos unos minutitos próximos.
Obrigado.
Muchas gracias, Lucas. Muchas gracias, Lucas, por la charla. Saludos, Daniel.
Gracias, gracias.